This video covers section 6.7, variation in problem solving. Our goals for this video are to solve problems involving direct, inverse, and joint variation. Let's start off with a little bit of exploration. Say that you work at a job where you're paid $10 an hour. What's the relationship between your total pay and the number of hours that you work? We could start by defining some variables here. Say H equals hours worked, and P can be total pay. Then the relationship between the hours that you work and the amount of pay that you get is P equals 10 times H. That is, your total pay is $10 times the number of hours that you work. This is an example of direct variation. In direct variation, when one variable increases, so does the other variable. When one variable decreases, so does the other. So the more hours you work, the more pay you get, and the fewer hours you work, the less pay you get. In any direct variation problem, the two variables you have are always related in the same way. You might have y equals some number times x, or y equals some number times x squared, or y equals some number times the square root of x, and so on. The big deal is that all of the variables are on the same level, so the y and the x are on the same level of the equation, and nothing is being divided by a variable. Notice that each of these equations has a k in it. That k isn't a variable, it's a constant. We call it the constant of variation, or sometimes the constant of proportionality, or the proportionality constant. In the example where you were paid $10 per hour, the 10 was the constant of variation. A problem that wants you to use direct variation might say it in a few different ways. You could say y varies directly with x, y varies directly as x, y is directly proportional to x. All of those mean that you're going to be using some kind of direct variation. Let's look at an example. The cost of tuition at LBCC is directly proportional to the number of credits taken. If 4 credits costs $395.80, find the constant of variation and the variation equation. Because this problem says that the cost of tuition is directly proportional to the number of credits taken, I know that I have an equation like y equals k times x. And I'm going to go ahead and say that y will be the cost of tuition, and x can be the number of credits. Because this problem tells me that one thing is directly proportional to another thing, I know that I have an equation where both my variables are on the same level. I can always go ahead and pick the first thing to be my first variable, and the second thing to be my second variable, but ultimately it doesn't really matter that much. Now the problem is asking me to find the constant of variation and the variation equation. Finding the constant of variation means figuring out what that k is. Now they've given me a little bit of information. They've told me that if I take 4 credits, it costs $395.80. So I can plug that 4 credits in for x and the $395.80 in for y, and then solve for k. Once I've filled in the information that I know, with x is 4 and y is $395.80, I can solve this equation for k, in this case by dividing both sides by 4. That tells me that k is $98.95. So now I've found k, which is my constant of variation. I've done the first part of this problem. The second part says to find the variation equation. Now we've actually already done all the work for this. We just need to write it down. My variation equation is y equals 98.95x. Now that I have this equation, I could use it to find out how much it will cost to take any particular number of credits. So I could plug in x equals 10 and find out how much it costs to take 10 credits, or x equals 12 and find out how much it costs to take 12 credits. In fact, that's the next thing that this question is going to ask us to do. Now we're going to use our equation to find the cost of taking 12 credits. So remember, my equation was y equals 98.95x, where x is the number of credits and y is the cost. So I'll just plug 12 in for x and find out what y is. So it looks like when you take 12 credits, it costs $1,187.40. Let's do another example. This one says, the weight of a rubber ball varies directly with the cube of its radius. A ball with a radius of 2 inches weighs 1.2 pounds. Find the weight of a ball with a radius of 3 inches. So the first thing that I notice is that this says the weight of a rubber ball varies directly with the cube of its radius. Those words, varies directly, tell me that the first thing I'm going to be doing is trying to write down a general variation equation. The problem says the weight of a rubber ball varies directly with the cube of its radius. That tells me everything that I need to know to write down my general variation equation. I have two variables, the weight and the radius, and they vary directly. That means that they'll be on the same level of my equation. So I can write down something like W equals K times R cubed. Now let's dissect that a little bit. W is the weight of my ball. It varies directly, which means that both my W's and my R's will be on the same level of my equation, with the cube of the radius. So I have the radius being cubed. And then because this is a variation problem, I've got my constant of variation, even though I don't actually know what that number is yet. Now that I've written down my general variation equation, my next step is to actually find that constant of variation and write down the specific variation equation. To do that, we just plug in the information that we've been given for W and R and solve for K. We know that a ball with a radius of 2 inches has a weight of 1.2 pounds. So I plug that information into my equation. 1.2 for the weight, K, still don't know what that is, and my radius is 2. And then it's being cubed because the weight varies directly with the cube of the radius. Now we go ahead and solve that equation for K. I get 1.2 equals K times 8. Divide both sides by 8, and we'll find that K equals 0.15. Now I can write down an equation that relates the weight with the radius. I can say W equals 0.15 times the radius cubed, now that I know what the K is. Finally, my last step is going to be to actually use this equation that we've invented to find the weight of the ball when the radius is 3 inches. So we know now that the weight of the ball equals 0.15 times the radius cubed. And I would like to find the weight of a ball with a radius of 3 inches, so I just plug 3 in for the radius and find out what the weight is that goes with that. So it looks like for this particular type of rubber ball, if it has a radius of 3 inches, it will have a weight of 4.05 pounds. Remember that in direct variation, when the value of one variable goes up, so does the value of the other variable. So for instance, in our examples, when the number of credits you took went up, the cost of the tuition also went up. Or when the radius of the ball got bigger, the weight of the ball also went up. Now we're going to look at what to do if we want the opposite sort of relationship. For example, maybe you have another job where you're going to get paid $100 no matter what, as long as you finish the job. We want to figure out what the relationship is between the amount you end up earning per hour and the total number of hours that it took you to complete the job. Let's say that H is the number of hours it takes, and P can again be your pay per hour, so your hourly rate. In this case, the longer you work, the less you're making per hour. If it takes you 100 hours to finish the job, you only got paid $1 per hour, which isn't really very good. But if you were able to finish the whole job in 1 hour, you got paid $100 per hour, which is pretty great. We can write that relationship down in an equation by saying that your pay per hour is that $100 divided by the number of hours that it takes you to complete the job. This is an example of inverse variation. The more hours you work, the less you're getting paid per hour. And the more you're getting paid per hour, the less hours you actually worked. When one goes up, the other one goes down. And when one goes down, the other one goes up. Whenever you have two variables related inversely, the equations will look like this. You'll have one variable on one level and another variable on the bottom, but also a constant of variation. Here I have y equals some number divided by x. Here I have y equals some number divided by x squared. Here I have y equals some number divided by the square root of x, and so on. The big key here is that the two variables are on opposite levels of the equation. One variable is always being divided by. My x is always on the bottom of a fraction. Again, you might see this referred to in many ways. Y varies inversely with x, or y varies inversely as x, or y is inversely proportional to x, or y varies inversely with x squared, and so on and so on. Let's look at an example. Because it's more efficient to produce large numbers of items, the cost of producing a floppy disk is inversely proportional to the number produced. That means if we make a whole lot more, it's actually cheaper to make each one. So if 4,000 disks can be produced for a cost of $1.20 each, find the constant of variation and the variation equation. Then use your equation to find the cost per disk when 6,000 are produced. Our first step is to write down a general variation equation. So to do that, we need to figure out how to unlock this code. We know that the cost of producing a floppy disk is inversely proportional to the number produced. That tells me my equation is going to look something like y equals k over x. That inversely proportional tells me that my second variable is in the denominator of a fraction. I also know what these variables are. My first variable, y, is going to be the cost of producing a floppy disk, and my second variable will be the number of floppy disks produced. Now that I have a general variation equation, my next step is to actually solve for k using the information that I've been given. So they told me that 4,000 disks can be produced for $1.20 each. So I plug that information into my equation and then solve for k. $1.20 is the cost, so that's my y. $1.20 equals k, which I still don't know, over x, which is 4,000. Now in this case, I can solve for k by clearing the fractions, multiplying both sides by 4,000, or you can think about cross-multiplying if you want to, and we'll end up with k equals 4,800. That means that my variation equation is y equals 4,800 over x. My last step now is to use my equation to answer the question. So I'm going to take my equation, cost equals 4,800 divided by number of disks made. I'm being asked to answer the question, if I produce 600 disks, what's the cost per disk? So I take my 6,000, plug it in for x, and then see what my y turns out to be. Looks like 80 cents. So if you're producing 6,000 disks, it only costs 80 cents per disk. Let's look at another example. This one says the intensity of light varies inversely as the square of the distance from the light source. At 2 feet from a light, the intensity of the light is 80 foot candles. How far away from the light do you need to be for the intensity to be 50 foot candles? Our first step is to write down a general variation equation. So this tells me that the intensity of the light varies inversely as the square of the distance. So my two variables here are the intensity of the light and the distance is going to be squared in my equation. The intensity and the distance vary inversely, which means that my second variable, the distance, is going to be on the bottom of my equation. I'm going to write this down as I equals k over d squared. So my intensity is here, my distance squared is on the bottom, and my constant of variation stays in the numerator of my fraction. And then as long as we're at it, we might as well write down what those variables mean. I is the intensity of the light, and d is the distance. Our second step is to solve for k and then write down what the variation equation really is. Now I've been told that at 2 feet from the light source, the intensity is 80 foot candles. So I can plug 80 in for my intensity. Still don't know what the k is, but my distance is 2 feet, so I plug 2 in for d. Now I can solve for k. Now we can go ahead and solve this equation for k. On the bottom here, I end up with 4, so 80 equals k over 4. I can cross multiply or think about clearing the fractions. In this case, I clear the fractions by multiplying both sides by 4, and that gives me k equals 320. And then finally, I actually write down the variation equation, which is, for me, intensity equals 320 over d squared. This is what we mean when we ask you to write the variation equation. You'll find the constant of variation, that's the number, and then the variation equation is all of it put together. Now my third step is to use the equation to answer the question. So the question asks, how far away from the light do you need to be for the intensity to be 50 foot candles? Now we've already gone to the trouble of making this equation that relates intensity and distance. They've just told me that the intensity is 50. So I plug 50 in for I, and I get 50 equals 320 over d squared. What we have now is a nice little rational equation. All we need to do to clear the fractions is multiply both sides by d squared. That gives me 50d squared equals 320. Now I'll solve for the d squared, dividing both sides by 50, to get d squared equals 6.4. To undo the squaring on the d squared, we'll take the square root of both sides, and we'll find that d is the square root of 6.4. Now this is the nice exact answer, but let's go ahead and get a nice decimal approximation for that. This is about the same as 2.5 feet. So in order for the intensity to be 50 foot candles, you'd have to be about 2.5 feet away from the light, which makes a certain amount of sense since at 2 feet it was 80 foot candles. So if you get a little farther away, that'll make the intensity a little less too. The last kind of variation that we have is called joint variation, and this is when a relationship has more than two variables. For example, the relationship between distance, speed, and time. You probably know that distance equals rate times time, where rate is your speed, time is how long you've been going that speed, and distance is how far you've traveled. We could say distance varies jointly as rate and time. Another example you're probably familiar with is the area of a triangle. Area is 1/2 base times height. The area varies jointly as the base and the height. In this case, the constant of variation is 1/2. Whenever you read varies jointly, you can think direct variation, but there happens to be more than one letter. Let's look at an example. The number of cars manufactured on an assembly line at GM varies jointly as the number of workers and the time they work. And then we've got a bunch of other information about how many workers can produce so many cars in so many hours. But let's start by doing our first step, which is writing down a general variation equation. Let's read through that important part again. The number of cars manufactured on an assembly line varies jointly as the number of workers and the time that they work. That tells me all of my important features. The number of cars varies jointly, so it'll equal something with a k in it. Because it says varies jointly, I know that my other variables will be going on the same level here because it's still direct variation. So varies jointly as the number of workers, so I need a variable for number of workers, and the time that they can work. So I need a variable for time. So again, when I read that initial information, I was able to say the number of cars varies jointly as the number of workers and the time they work. So the number of cars, the number of workers, and the time will be my three variables. Because they vary jointly, they really are varying directly. So they'll all be on the same level of this equation. And there's got to be a constant of variation in there as well. My next step is to use some of the information that they gave me to find the actual value of k and then write down the variation equation. So they tell me that 200 workers can produce 60 cars in 2 hours. So I'm going to plug all that information into my equation here. Let's see, I have 200 workers, 60 cars, so 60 goes in for C. Don't actually know what the K is. W is my workers, so 200 workers. T is my time, so the 2 hours goes there. Now I can solve for K. 60 equals 400K. Divide both sides by 400, and K equals 0.15. That means that my variation equation is C equals 0.15 times W times T. My last step is to use that equation that we just made to answer the question. This wants to know how many cars can 240 workers make in 3 hours. So C is my cars, don't know that one yet, 0.15. W is the number of workers, so 240 goes in there. T is the time, so 3 hours goes in there. And then I just multiply these numbers together and I get that the number of cars that they should be able to make is 108 cars. Now we're going to do one big example where we put everything together. There's 3 things that'll help you out when you're working on these problems. You're always going to have a K, and the K is always going to be on the top of the fraction if there's a fraction. Anything that varies directly or is direct in any way will go on top with the K. and anything that is inverse is going to go in the denominator underneath the k. Here's our big example. The maximum load a rectangular beam can support varies jointly as its width and the square of its height, and inversely with its length. Step 1 is to write down the variation equation. I've been told that the maximum load a certain type of beam can support varies jointly. Remember, jointly really means directly with more variables. So the maximum load varies jointly as the width and the square of its height, and inversely with its length. Okay, we're going to tear this all apart here. Maximum load, let's call that M. The maximum load varies whatever. So that's going to be equal, and I'm going to have a K somewhere in there. It'll be in the numerator of my fraction if I end up with a fraction. The maximum load varies jointly with the width and the square of its height. Because varies jointly really means directly, but with more than one variable coming afterwards, I'm going to put the width and the square of its height up here in the numerator with the K. Width can be W, and height can go ahead and be H. Now, because this says the square of its height, I know that the height will need to be squared. And finally, then, we've got inversely with its length. Let's call the length L, because it varies inversely with the length. The length goes on the bottom of the fraction. Now that we've got our variation equation written down, let's go ahead and take a moment and admire it. What we have here is the maximum load of our beam varies jointly with the width and the square of its height. So the width and the square of its height go up top along with the constant of variation k, and inversely with its length. So the length goes on the bottom. Notice that this means that when the width or the height of the beam, this part of it, get bigger, the maximum load that it can bear gets bigger, which kind of makes sense. As you make the beam wider, it should be able to support more weight. But when we make the length longer, then the maximum load will go down, which again, I think sort of makes sense. If you make a beam really long, it's not going to be able to bear as much weight. Our next step, of course, is going to be to use some information to actually find the constant of variation k and write down a variation equation. Remember that our general equation that we just came up with was m equals k wh squared over L. Now they're telling us that a beam that's a 1/3 foot wide, 1 foot high, and 10 feet long can support 3 tons. We can use that information to figure out what k is. The 3 tons is the maximum load, so 3 goes in for the m. K is our constant of variation that we're trying to find. The width is 1/3 foot. The height is 1 foot. And the length is 10 feet. So we plug all that information in here, and then we're going to solve for k. The first thing that I'd like to do is multiply both sides by 10 to clear the fractions a little bit. Multiply both sides by 10, and now I have 30 equals 1/3 times k. Notice that I don't need to keep writing that 1 down. Now I have 30 equals 1/3 of k. Again, I have a fraction, so let's go ahead and multiply by 3 to clear that fraction. That gives me k equals 90. Now I can write down my variation equation. M equals 90 times the width times the height squared all over the length. There's my variation equation. Finally, our third step is to use the equation to answer a question. This one wants to know, how much weight can a similar beam support if it is 1 foot wide, a 1/3 foot high, and 9 feet long? So we take these 3 numbers, plug them into our equation, and solve for the maximum load. So m is 90 times 1 foot of width, 1/3 squared for the height, and 9 feet long. Now we'll go ahead and just plug that into our calculator and come up with a nice number. This comes out to be 10/9, or a little bit more than 1 ton. Now that kind of joint variation problem is about the most complicated that these variation problems will get. So what I have now are a couple of simpler variation problems for you to try. Go ahead and pause the video and see what you can do with this variation problem. Suppose y varies directly to x. If y is 24 when x is 8, find the value of y when x is 5. Remember, your 3 steps are to write down your variation equation, solve for the constant of variation, and then use your equation to answer the question. Pause the video and give it a try. And we're back. So your first step is to write down a general equation. This says, suppose y varies directly to x. So one of my variables is y, it's varying directly, and my other variable is x. So that tells me I have a y, an x, and a k, and everything is on the same level here. My second step is to find k and write down the variation equation. I've been told that y is 24 when x is 8. So I plug in an 8 for x and a 24 for y, solve for k. My constant of variation then is 3, and my equation altogether is y equals 3x. Lastly, I'll use my equation to answer the questions. They want me to figure out the value of y when x is 5. So I plug 5 in for x, and I find that y is 3 times 5, which is 15. I have one more problem for you to try. This time we have y varying inversely to x. Go ahead and go through those same 3 steps, write down your general variation equation, figure out what k is and what your variation equation is, and then use your equation to answer the question. Go ahead and pause the video and give it a shot. And we're back. So this problem says that y varies inversely to x. So in our first step, when we write down the general variation equation, we're going to have y equals k over x. Because we're varying inversely with x, the x goes on the bottom of the fraction, but we still need our constant of variation in there. Next up, we find k and write down our variation equation. We've been told that when y is 6, x is 3. So I'll plug in 3 for x and 6 for y to get 6 equals k over 3. I can multiply both sides by 3 to get 18 equals k. There's my constant of variation. To write down my variation equation, though, I want to put all that information together and write y equals 18 over x, now that I actually know what k is. Finally, we'll use the equation to answer the question. The question is asking, find the value of y when x is 9. So I take my equation, plug in 9 for x, and find that y equals 2. Lastly, I'd like you to go ahead and look at each of these equations and decide whether it represents direct, inverse, or joint variation. Go ahead and take a moment to do that, maybe pause the video, and then we'll come back and talk about each one. Alright, are you ready to look at these guys together and decide which equations represent direct variation, which one's inverse variation, and which one's joint variation? What I want to do is go through and start by looking for everything that represents joint variation. Remember, joint variation means that there's more than one variable. Multiple variables. So let's just go through and look at each one to see which ones could be joint variation. Here I have y equals x, only 2 variables. Y equals t, only 2. Y and a z, only 2. Aha! Here we have 2 variables on the right-hand side, both an m and an n. That makes this one joint variation. Over here I've got a y and an x, a y and an a. Aha! Here I have an a and a b, so this one is also joint variation. And then here I have a y and a z. So those are the only 2 examples of joint variation on this page. Next, let's go through and look for direct variation. Remember that in direct variation, I'll have something like y equals 4x, or y equals some number times x. Something like this. This first equation almost doesn't look like direct variation, but it is, because the x is not in the denominator. The y and the x are on the same level. It's just that the constant of variation happens to be a fraction. So this one is direct variation. Here, the t, the other variable, is in the denominator, which makes this not direct variation. But here, y equals 45z certainly is direct variation. Here again, my variable is in the denominator, so it's not direct variation. And then here with my y equals 5/3 a, this one is direct variation. Again, it's kind of like my first example. Even though the constant of variation is a fraction, the y and the a are still on the same level, and we're not dividing by a variable. So this is direct variation as well. And then here with y equals 5 over z, that z is in the denominator, which makes it not direct variation. Last up, let's make sure that everything that's left really is inverse variation, and we haven't missed anything. So inverse variation means you'll be dividing by a variable, something like y equals k over x. Here I have a number being divided by my variable, which makes this inverse variation. Again, here the variable is in the denominator, so this is inverse variation. And again, y equals 5 over z. The variable is in the denominator, which makes this inverse variation. And now I think we've classified all of these guys as either direct, inverse, or joint variation. That wraps up section 6.7, variation problems. So go ahead and get started on your homework, and I'll see you in class.